All right, this is MAT221, Calculus 1. We're in section 4.1 talking about applications to the derivative, talking about the topic of related rates. Now, we were talking about this water is draining from a cylindrical tank that is at a rate of 3 liters per second, and how fast of the surface of the water is dropping. We took the derivative of the volume equation with respect to time, remembering that both pi and r squared were going to be thought of as numbers or constants. And remember, we're going to use the constant multiple rule and just pull those constants out to the front. So even though r squared looks like a variable, we're treating it as a constant because the radius of this tank will never change. It is a constant number, whatever it happens to be. All right. So then what we do next is once we have this implicit differentiation done, we replace what we know. So we know that the rate of change in the volume is negative 3,000 centimeters cubed per second. So I can take this number and replace it into this equation for dV dt. R was thought of as a constant. When I do, I get this equation. And now we're going to solve for what we want to find. We want to find what is the rate of change in the height with respect to time. So we solve for dH dt, and we get negative 3,000 centimeters cubed per second over pi r squared. Now we don't know what the radius of this tank is, but we know no matter what the tank is, once we find out the radius, we know that the height of the water will be changing at this particular rate, no matter whatever our radius happens to be. Now it looks complicated here, but this is our answer for our rate of change. So here's our steps for related rates problem, and we're going to do a bunch of these. There's a bunch in this particular PowerPoint, and then I'm going to do a bunch more on some worksheets that we have. So here's our steps. We draw a picture if we can and try to sketch the situation if it's not given to us. Next, we try to write down any information that they gave us from the few sentences that we get. Step 3, we try to write down what are we looking for, and it's usually a derivative. Next, we write down an equation that will relate these variables. Next, we differentiate both sides of this equation that we found with respect to time. And lastly, we evaluate to get what we're looking for in step 3. Now it seems like really simple, these steps, but they are not. And it's just like any other word problem. If we don't begin in the right direction, when we go down the wrong path, these can become very difficult problems. So we're going to try a bunch more of these, and I'm going to have a couple of worksheets that I'm going to work through with you too in this worksheets folder for this unit. But for right now, let's look at another classic problem that we might see. This is the classic what's called hot air balloon problem. Now, if we're given that at this particular point in time, say I'm over here, I'm sitting here with my camera, I'm 500 feet from the launch site of a hot air balloon, and my arm is swinging up with my camera to take a picture of the balloon, where theta is the angle between the horizontal and my line of sight. If at this particular point in time, the angle is 45 degrees or pi on 4 radians, and I know that I'm 500 feet from the launch site, and I know that my arm is swinging or the angle is changing by 0.14 radians for every minute as the balloon rises, how fast is the blue balloon actually rising? In other words, what is the rate of change in the height with respect to time? They're asking me to find what is my dH dt? What is my rate of change in the height with respect to time? Now, we have to somehow come up with a formula to relate h and theta, because those are our two variables here. This side right here, the 500, is not a variable. That is just 500. So how do I do that? Well, I could use tangent, because if we know in a right triangle, the tangent ratio says that the tangent of the angle theta is equal to opposite over adjacent. So I could say, well, tangent theta equals h over 500. All right, so now I have an equation that relates theta and h. Let's take the derivative of this expression with respect to time. When I do, I'm going to be using the chain rule. I take the derivative of the outside piece, derivative of tangent is secant squared, leaving the inside function alone, theta, times the derivative of the inside function with respect to time, which is d theta dt. Now I take the derivative of this side. Now remember, this is just 1 over 500 times h. So the derivative is just going to be 1 over 500 is a constant. I'm going to pull it to the front. And then I'm going to take the derivative of h with respect to time, which I don't know what that is, so I say dh dt. Now, what information do I know? This is the only information I know right here. I know that d theta dt, I know that one, I could plug that in. But I want to solve for dh dt, but I don't know what the secant of theta is. But I probably could figure it out. At this point in time, theta is pi on 4. So I could figure out what this is. Secant of pi on 4 is actually the reciprocal of the cosine of pi on 4. And then I'm going to square it and multiply it by 0.14 radians per minute. When I do, and I get my secant of pi on 4 is equal to radical 2, which is the reciprocal of the cosine function, then I'm going to square that and put this into the equation and get 140 feet per minute is my units here when I put my units in with dimensional analysis. So I multiply radical 2 squared times 0.14 times 500 to get 140 feet per minute. This is how fast the balloon is rising at this particular instant in time. Let's look at another problem. Say we have two trucks. Truck A heads east from an intersection at 40 miles per hour. Truck B heads straight north from the intersection at 30 miles per hour. How fast is the distance between the two trucks changing 6 minutes later? All right, let's see if we can put this together. We know that rate equals distance equals rate times time. So we know that if I travel 40 miles per hour for 6 minutes, which is equal to 1/10 of an hour, that gives me 4 miles. So if I go 40 miles per hour times 1/10 of an hour, I've gone 4 miles. So truck A has gone 4 miles in the easterly direction from my intersection after 6 minutes. Now, truck B is traveling north and is going 30 miles per hour. So if we do 30 miles per hour times 1/10 of an hour, 6 minutes is 1/10 of an hour. That is 3 miles. I've gone 30 miles per hour times 1/10 of an hour. That gives me 3 miles. So truck B is going directly north 3 miles after 6 minutes. So after 6 minutes of time, this is where my trucks look like they are after 6 minutes. I want to know what's the rate of change, how fast is the distance between the trucks changing? Now mind you, remember I could say here, right, the distance between the two trucks is when this truck is here and this truck is here, right? It's going to be the hypotenuse of this triangle as the trucks move in each direction. So it's like a triangle that's getting bigger and bigger and bigger. So there is the distance between those two trucks. At this particular instant in time, I can figure out how far away they are from each other. If I do the Pythagorean theorem, 3 squared plus 4 squared equals 5 squared. So I know that z at this particular time instant in time, 6 minutes after the trucks left, I know that at this particular instant in time, the trucks are 5 miles apart. Okay. Now, let's look at this problem. We want to know what's changing. Well, X is actually changing. At this particular point in time, X is 4, 6 minutes after. And at this particular point in time, Y is equal to 3. But Y is changing and X is changing, and so is Z. So when things are changing, we use them as variables. We state them as variables. So X will be our horizontal distance, or our distance that truck A travels. Y will be our vertical distance, or the distance truck B travels. And Z will be the distance between the two trucks. In this particular instance, this is equal to 5. Okay, we know that these three things can be related using the Pythagorean theorem. So we're relating X, Y, and Z using the Pythagorean theorem in this case. X is changing, Y is changing, and Z is changing. So they all are thought of as variables. So let's take the derivative with respect to time. So again, let's use implicit differentiation. The derivative of x squared with respect to t, x is not equal to t, so we take the derivative using the chain rule. The 2 comes to the front, leave the inside function alone of x, subtract 1 from the exponent, we get 2x. Times the derivative of the inside function with respect to time. I don't know what that is, so I say dx dt. Plus, let's move to the next part of the function. Again, we're taking the derivative with respect to time. This does not equal t, so we're going to take the derivative implicitly. The 2 comes to the front, leaving the inside function, subtract 1 from the exponent, done, derivative, times the derivative of the inside function with respect to time. I don't know what that is, so I simply write implicitly dy dt. And likewise, z, I get 2z dz dt. In this particular case, I could divide everything by 2 and get our resulting equation. I know in this particular instance what the rate of change is in the x direction. Remember, x direction was truck A, and we know how fast, or the instantaneous rate of change. We know the derivative there. The derivative of x with respect to t is simply the rate of the truck A and how fast the truck A is traveling. We know also that truck B is traveling at 30 miles an hour. We do not know how fast the distance between the two trucks is changing. That's what we have to find. That's our question mark. So by substituting these values in here, we have 4 for x, 40 for y, 40 for dx dt, 3 for y, 30 for dy dt, 5 for z, but the only thing we don't know is what they're asking us for. How fast is the distance between the trucks changing? What is the rate of change of z? Solving, we get 50, and we put in our units. The trucks are changing at an instantaneous rate of change at 50 miles an hour. The distance between them is changing by 50 miles per hour after the trucks have been driving for 6 minutes. All right, this is the end of this PowerPoint. However, I have several more lessons that we need to do on related rates. This is a really tough topic. So I'll be back with a couple more videos going through some of the worksheets that are in the worksheet folder for section 1.4. Have a good day.